Welcome to another journey through the cosmos. Tonight I'll be telling you about the storms inside Saturn's atmosphere, beginning at the cloud tops and taking you on a journey that will lead us deeper and deeper, not just into Saturn itself, but into the very nature of our solar system, the stars, and the universe beyond. But before we begin, let me tell you what to expect. This video is designed to help you fall asleep peacefully. You'll hear my voice guiding you through Saturn's turbulent atmosphere, down through layers of clouds and gas, into the planet's mysterious interior, and then outward again to explore the cosmic context that makes Saturn what it is. And then, once the story ends, you'll hear brown noise for the rest of the night. Brown noise is a deep, low-frequency sound, like distant thunder or ocean waves, that helps mask background sounds and keeps you in deep sleep throughout the night. So get comfortable, close your eyes, and let's begin our journey into the heart of Saturn and beyond. Right now, at this very moment, 1.5 billion kilometers from where you're lying, a storm larger than Earth itself is raging across Saturn's atmosphere. Winds howl at 1,800 kilometers per hour. Lightning bolts 1,000 times more powerful than anything on Earth crack through the churning clouds. Thunder rolls across thousands of kilometers of alien sky. This is just one storm among countless others swirling through Saturn's golden atmosphere. And tonight we're going to descend into these tempests, following them down through layer after layer, deeper into the planet, and then beyond, tracing the connections that link this distant world to everything else in the cosmos. Close your eyes, take a deep breath, and prepare to fall into Saturn. Let's begin at the cloud tops, where Saturn's atmosphere first becomes visible to our telescopes here on Earth. From our vantage point, Saturn appears as a serene golden sphere marked with subtle bands of cream and tan, encircled by its magnificent rings. But this tranquil appearance masks a world of violent motion. The entire atmosphere is in constant flux, churning with storms and winds that dwarf the most powerful hurricanes Earth has ever known. The bands you see stretching across Saturn's face are jet streams, rivers of wind flowing around the planet at different latitudes. Near the equator, the winds blow eastward at nearly 500 meters per second, creating a jet stream faster than the speed of sound in Earth's atmosphere. These aren't temporary weather patterns. They're permanent features of Saturn's atmospheric circulation, driven by heat rising from deep within the planet and organized by Saturn's rapid rotation. The planet completes one full rotation every 10.5 hours, making a day on Saturn less than half as long as a day on Earth, despite Saturn being 9 times wider than our world. This rapid rotation creates powerful Coriolis effects that organize the atmosphere into distinct bands of alternating wind direction. At some latitudes, winds blow eastward. At others, they blow westward. And where these opposing wind streams meet, turbulence forms. Eddies spin off. Vortices develop. Storms are born in the shear zones between these jets, fed by energy rising from below and organized by the planet's rotation into coherent structures that can persist for months or even years. Some storms on Saturn are small and short-lived, lasting only days before dissipating. Others are enormous and persistent. The largest storms appear roughly once every 30 Earth years, coinciding with Saturn's northern hemisphere's summer. These great white spots, as astronomers call them, are massive convective outbursts that erupt from deep in the atmosphere, punching through all the cloud layers and spreading across vast regions of the planet like massive white scars against the golden clouds. In December 2010, amateur astronomers noticed a small bright spot appearing in Saturn's northern hemisphere. Within weeks, it had exploded into an enormous storm system that wrapped completely around the planet, creating a turbulent band of clouds more than 300,000 kilometers long. That's long enough to stretch from Earth to the Moon and back again with distance to spare. The storm raged for months, lightning flashing through its depths at a rate of 10 strikes per second, creating radio emissions so powerful they could be detected from Earth across 1.5 billion kilometers of space. But what you see from above is only the beginning of the story. The cloud tops are merely the surface, and to truly understand these storms, we need to descend into them. We need to follow the churning currents down through the atmosphere, down into regions where the pressure rises and the temperature climbs, down into depths that no spacecraft has ever directly observed. So let's begin our descent now, falling gently through the thin upper haze into the first layer of Saturn's cloud deck. The uppermost clouds are made of ammonia ice crystals, forming at the frigid temperatures of Saturn's high atmosphere, where it's about negative 140 degrees Celsius. This is where Saturn gets its characteristic golden color, though the exact chemical compound responsible for the hue remains a mystery. Scientists suspect it might be phosphorus compounds or complex organic molecules created when sunlight interacts with methane and ammonia high in the atmosphere, but we don't know for certain. As we descend through these ammonia ice clouds, the air around us grows denser and the pressure steadily increases. We're falling through a region of intense vertical motion. Here in the heart of a storm, warm gas rises from the depths while cooler gas sinks from above, creating powerful updrafts and downdrafts. These vertical winds can exceed 100 meters per second, faster than the most violent tornadoes on Earth. Ammonia ice crystals are caught in these currents, swept upward and downward, colliding with each other, sticking together, growing larger until they become heavy enough to fall as ammonia snow, descending toward the warmer layers below, where they'll evaporate and be carried upward again in an endless cycle of condensation and evaporation. Lightning illuminates the clouds around us as we fall. Saturn's lightning is different from Earth's in important ways. On our planet, lightning typically strikes from cloud to ground, following the path of least electrical resistance through the atmosphere. But Saturn has no solid ground for lightning to strike. Instead, electrical discharges arc between clouds or within clouds, following paths through regions of differing electrical charge. Each bolt releases tremendous energy, as much as a small nuclear explosion, heating the surrounding gas to tens of thousands of degrees in a fraction of a second, and creating thunder that would be deafening if there were anyone here to hear it. We continue our descent. The ammonia ice clouds gradually thin and disappear as we fall into warmer temperatures where ammonia can't freeze. Now we're passing through a relatively clear zone, a layer of atmosphere that's largely cloud-free, stretching downward for many kilometers. The pressure here is about 1 bar, similar to Earth's atmospheric pressure at sea level, but the temperature is still well below freezing at around negative 100 degrees Celsius. If you could somehow survive here with appropriate protection, you'd see clouds above you and clouds below you, but the air immediately around you would be relatively clear, glowing with a dim golden light filtering down from the sunlit upper atmosphere. But we're not stopping here. We keep falling, and soon we encounter the next major cloud layer. These clouds are composed of ammonium hydrosulfide, a compound formed when ammonia reacts with hydrogen sulfide. They condense at temperatures around -50 degrees Celsius and pressures of several bars. The clouds here are thicker and more substantial than the ammonia ice clouds above, and the storms are more intense. The temperature continues to rise as we descend, warmed both by the increasing pressure of all the atmosphere above us and by heat flowing upward from Saturn's interior. This is a crucial point to understand about Saturn. The planet radiates more energy into space than it receives from the Sun. Unlike Earth, which is warmed primarily by solar radiation, Saturn glows with its own internal heat. This heat is a remnant from the planet's formation 4.5 billion years ago, when gravitational energy was converted to heat as material collapsed to form the planet. But there's another source of internal heating as well, one we'll discover as we descend deeper. Helium is slowly separating from hydrogen deep in Saturn's interior and raining downward toward the core, releasing gravitational potential energy that adds to the planet's heat output. This internal heat drives convection throughout Saturn's atmosphere and interior. Warm material rises, cool material sinks, creating vast circulation patterns that transport heat from the depths to the surface where it radiates into space. This convection is what powers the storms we're descending through. Heat rising from below creates instability in the atmosphere, and when that instability is released, storms erupt. As we fall through the ammonium hydrosulfide clouds, we can feel the turbulence intensifying around us. We're deep inside the storm now, surrounded by churning gases, buffeted by updrafts and downdrafts. The clouds are dark here, blocking most of the sunlight from above, and the only illumination comes from the constant flicker of lightning and a faint glow of heat from below. This is an alien environment, hostile to any form of life we know, yet it's governed by the same physical principles that create weather on Earth: heat, pressure, rotation, and the behavior of gases under different conditions. We continue downward. The ammonium hydrosulfide layer gives way to another clear zone, and then we approach the deepest and most important of Saturn's cloud layers, the water clouds. These form at depths where the pressure reaches 10 to 20 bars and the temperature climbs above the freezing point of water. Here, remarkably, liquid water droplets can exist, suspended in clouds that stretch across thousands of kilometers of Saturn's deep atmosphere. This is where the most powerful storms originate. When water vapor condenses into liquid droplets, it releases latent heat, the energy that was required to evaporate the water in the first place. This heat makes the air more buoyant, causing it to rise even more rapidly, which draws in more moist air from below, which condenses and releases more heat, creating a positive feedback loop. This is the same process that powers thunderstorms on Earth, but on Saturn, it operates at a much larger scale, with much more energy available. The great white spots we mentioned earlier originate here in the water cloud layer. Massive convective towers punch upward from these depths, carrying water vapor and heat up through all the layers above, breaking through into the upper atmosphere where they spread out and become visible as enormous white plumes against Saturn's golden clouds. These storms can release as much energy in a few months as a major hurricane on Earth releases in its entire lifetime, and they can affect atmospheric circulation patterns across half the planet. But our descent doesn't stop at the water clouds. We're going deeper still, falling into regions where clouds no longer form because the temperature and pressure are too extreme. We're entering Saturn's deep atmosphere, a realm that has never been directly observed by any spacecraft, known only through theoretical models and indirect measurements from remote sensing. The pressure here is measured in dozens of bars and rising rapidly. The temperature has climbed to several hundred degrees Celsius, far above the boiling point of water. We're still surrounded by hydrogen and helium, the same elements that make up the sun, but here they're compressed by the immense weight of all the atmosphere above us. As we fall deeper, the pressure increases exponentially. At 100 bars, the temperature is around 300 Kelvin, roughly room temperature. At 1,000 bars, it's perhaps 700 Kelvin. The environment is becoming increasingly extreme. The boundary between atmosphere and interior begins to blur. On Earth, there's a clear distinction between the air and the ground beneath our feet. But Saturn has no solid surface. As you descend, the gas simply becomes denser and denser, transitioning gradually from a thin gas to a thick fluid, with no sharp boundary marking where atmosphere ends and interior begins. Planetary scientists have to choose somewhat arbitrary definitions. They might say the atmosphere ends where the pressure reaches a certain value, or where the density exceeds a certain threshold. But these are conventions, not natural boundaries. Let's say we've now entered Saturn's interior proper, having descended past the region anyone would reasonably call atmosphere. The pressure has reached thousands of bars. The temperature exceeds 1,000 Kelvin. We're surrounded by hydrogen, but it's not behaving like the hydrogen gas you might imagine from chemistry class. At these pressures and temperatures, hydrogen exists in a state between gas and liquid, a supercritical fluid where the distinction between the two phases disappears. And soon, as we continue our descent, something remarkable happens. Under the extreme pressure, hydrogen molecules begin to break apart. Normally, hydrogen exists as H pairs of hydrogen atoms bonded together. But as the pressure reaches about 1 to 2 million bars, roughly 20,000 kilometers below the cloud tops we started from, these molecular bonds can no longer withstand the compression. The molecules dissociate, and the electrons that were bound to individual atoms begin to behave collectively, moving freely through the material like electrons in a metal. We've entered the realm of metallic hydrogen, a phase of matter that doesn't exist naturally anywhere on Earth and can only be created briefly in the most extreme laboratory experiments. This is one of the strangest substances in the solar system, predicted theoretically long before it could be created or observed. It's called metallic hydrogen because it conducts electricity like a metal, even though it's still made of hydrogen atoms. This metallic hydrogen layer extends from about 20,000 kilometers, deep all the way down to Saturn's core, making up the bulk of the planet's interior volume and mass. And it's not static. The metallic hydrogen is in constant motion, convecting, flowing in complex patterns, driven by heat flowing upward from the core. This motion, combined with Saturn's rapid rotation, creates electrical currents that flow through the conducting fluid, and these currents generate Saturn's magnetic field through a dynamo process, similar to how Earth's liquid iron outer core generates our magnetic field. Saturn's magnetic field is substantial, though not as powerful as Jupiter's. It extends millions of kilometers into space, creating a magnetosphere that deflects the solar wind and traps charged particles. Interestingly, Saturn's magnetic field is almost perfectly aligned with the planet's rotation axis, tilted less than 1 degree. This is unusual. Earth's magnetic field is tilted about 11 degrees from our rotation axis, and Jupiter's is tilted about 10 degrees. Why Saturn's field is so well aligned remains something of a mystery. As we descend through the metallic hydrogen layer, the pressure continues its relentless increase. We're now experiencing pressures of millions of bars, forces that would instantly crush any material substance from Earth into a thin film. The temperature has climbed to thousands of Kelvin. Hot enough that the metallic hydrogen would glow if there were anyone to see it. Hot enough to vaporize any substance we're familiar with. The metallic hydrogen is turbulent, churning in complex convective patterns. Heat flows upward from Saturn's core, and cooler material sinks to replace it. This convection is what transports energy from the deep interior to the atmosphere, where it ultimately radiates into space. The flows are organized by Saturn's rotation into patterns that are difficult to visualize, but that can be modeled with sophisticated computer simulations. The metallic hydrogen doesn't flow uniformly. Instead, it forms columns or plumes aligned with the rotation axis, similar to the convective patterns in Earth's outer core, but on a vastly larger scale. Mixed with the metallic hydrogen is helium, and here in the deep interior, something interesting happens to that helium. At the pressures and temperatures found in Saturn's interior, helium becomes less soluble in metallic hydrogen. Think of it like oil and water separating. Helium-rich droplets begin to form and separate from the hydrogen. These droplets, being denser than the surrounding hydrogen, slowly sink toward the core. This process, called helium rain, has important consequences. First, it releases gravitational potential energy as the helium droplets fall, contributing to Saturn's internal heat. This is one reason why Saturn radiates more energy than it receives from the Sun. The planet is still slowly releasing the energy from its formation, and the helium rain process adds to this ongoing energy release. Second, it changes the composition of Saturn layers, depleting them in helium compared to the primordial composition the planet had when it formed. When the Cassini spacecraft analyzed Saturn's atmosphere during its 13-year orbital mission, it found that the helium abundance was indeed lower than expected, about half the value measured in the Sun's atmosphere. Since the Sun's composition represents the primordial composition of the solar system, this depletion suggests that helium has been removed from Saturn's upper layers, supporting the helium rain hypothesis. We're now deep within Saturn's interior, more than halfway to the center, falling through a region where helium droplets are constantly forming and sinking around us like rain, except this rain is made of liquid helium falling through metallic hydrogen at temperatures of thousands of degrees and pressures of millions of bars. It's rain that has been falling for billions of years, slowly redistributing helium within the planet's interior. As we approach Saturn's core, the environment becomes even more extreme. The pressure reaches tens of millions of bars, approaching 100 million bars near the core boundary. The temperature has climbed to perhaps 10,000 Kelvin, or even higher. These are conditions that exist almost nowhere else in the solar system except in the cores of other giant planets and in the interiors of certain stars. And now, after falling for what would be many hours if we were actually making this journey, after descending through thousands of kilometers of atmosphere and tens of thousands of kilometers of hydrogen interior, we finally reach Saturn's core. This is one of the least understood parts of the entire planet. We know a core must exist because Saturn's total mass and radius combined with our understanding of how hydrogen and helium behave under pressure, require a central concentration of heavier elements. But we don't know the core's exact size, precise composition, or detailed structure. Current models suggest Saturn's core contains perhaps 15 to 20 times Earth's mass, composed primarily of rock and ice, though at these temperatures and pressures, the term ice is misleading. The water, methane, and ammonia that we call ices were present when Saturn formed, but they've been subjected to such extreme conditions over billions of years that they've chemically transformed into exotic compounds and possibly superionic ices, strange states of matter, where oxygen atoms are locked in a crystalline lattice while hydrogen ions flow freely through the structure like a fluid. The core might not have a sharp boundary. Instead, there could be a gradual transition zone where heavy elements mixed with hydrogen and helium in varying proportions, creating a fuzzy boundary between core and envelope. Some recent models even suggest the core might not be entirely solid but could be partially or fully molten, a dense fluid of heavy elements at the center of the planet. The core likely has internal structure as well. The densest materials, iron and nickel, probably concentrate at the very center, surrounded by layers of lighter rocky materials like silicates, and then the ice-derived compounds in the outer regions of the core. But this is largely speculation based on theoretical modeling and comparison with what we know about terrestrial planets and other giant planets. What we do know is that this core formed first in the early solar system from the collision and gradual accumulation of planetesimals, rocky and icy bodies orbiting the young sun. Once the core grew to about 10 Earth masses, its gravity became strong enough to directly capture gas from the surrounding solar nebula, the vast disk of gas and dust from which all the planets formed. This gas accretion phase continued for perhaps a few million years until something ended it. What ended the gas accretion? Most likely it was the dispersal of the solar nebula itself. The young sun went through a phase called the T-Tauri stage, during which it generated powerful stellar winds and intense radiation that gradually blew away the remaining gas in the inner solar system. Once the gas was gone, Saturn could no longer grow by capturing more hydrogen and helium. The planet's growth stopped, and it has remained essentially the same size since then, though it has been slowly contracting and cooling over the intervening 4.5 billion years. We're now at the center of Saturn, at the deepest point of our descent, surrounded by exotic matter at extreme temperatures and pressures. This is as far down as we can go. But our journey through understanding Saturn doesn't end here. To truly comprehend this magnificent planet, we need to zoom back out and see Saturn in its broader context, as part of the solar system, as one of 4 giant planets, as a world that formed from the same material as everything else we see in our cosmic neighborhood. So let's begin our ascent, not physically rising back through the layers we descended through, but mentally expanding our view, pulling back to see Saturn not just as an isolated world, but as part of a family of planets orbiting the Sun. Saturn is the second largest planet in our solar system, surpassed only by Jupiter. It's a gas giant, a type of planet that's fundamentally different from the rocky terrestrial worlds like Earth, Mars, Venus, and Mercury. While terrestrial planets are made primarily of rock and metal with thin atmospheres, gas giants are made mostly of hydrogen and helium surrounding a relatively small rocky core. This difference in composition reflects where these planets formed in the early solar system. The inner solar system, close to the young sun, was hot. Too hot for hydrogen and helium to condense or for ices to form. Only rocky and metallic materials could exist in solid form there, so the planets that formed in the inner solar system incorporated only these materials. They became small, dense, rocky worlds. But beyond a certain distance from the sun, called the frost line or snow line, temperatures were cold enough for water ice to condense. This made much more solid material available for planet formation. Saturn formed beyond the frost line, at a distance where ices could condense. The cores of giant planets grew larger than terrestrial planet cores because they had access to icy materials as well as rocky ones. And once a core grew massive enough, about 10 Earth masses, it could gravitationally capture hydrogen and helium directly from the solar nebula, beginning a runaway process that continued until either the nebula dispersed or the planet's feeding zone was exhausted. Jupiter, being closer to the Sun than Saturn and in a denser part of the solar nebula, grew faster and captured more gas, becoming about 3 times more massive than Saturn. Saturn, forming farther out where the disk was less dense and perhaps forming slightly later, captured less gas before the nebula dispersed. This difference in formation history has consequences for both planets' present-day structures. Despite being less massive, Saturn has a lower density than Jupiter. In fact, Saturn has the lowest density of any planet in the solar system, about 0.7 grams per cubic centimeter on average. That's less dense than water, which means Saturn would float if you could find an ocean large enough to put it in. This low density comes from Saturn's composition, which is dominated by the lightest elements, hydrogen and helium, and from the fact that Saturn's lower mass means less gravitational compression of its interior compared to Jupiter. The other 2 giant planets, Uranus and Neptune, are different from Jupiter and Saturn in important ways. They're often called ice giants rather than gas giants because while they have substantial hydrogen and helium envelopes, they contain much larger proportions of heavier elements, particularly water, methane, and ammonia in their interiors. Their cores are thought to be larger relative to their total mass, and their hydrogen envelopes are much thinner than those of Jupiter and Saturn. Why are Uranus and Neptune so different from Jupiter and Saturn? The most likely explanation relates to when and where they formed. Uranus and Neptune orbit much farther from the Sun than Jupiter and Saturn, in regions where the solar nebula was even less dense and where planet formation took longer. By the time Uranus and Neptune's cores grew large enough to begin capturing gas, the solar nebula may have already been largely dispersed, so they captured much less hydrogen and helium than Jupiter and Saturn did. Or they may have formed closer to the Sun and later migrated outward through gravitational interactions with other bodies, a process that would have affected their gas capture. This leads us to an important realization. The solar system we see today is not exactly the solar system that originally formed. The planets didn't form in their current orbits and stay there unchanged. Instead, they migrated, moving inward or outward through gravitational interactions with the disk of material from which they formed and with each other. This planetary migration had profound effects on the architecture of the solar system. Computer simulations of solar system formation suggest that Jupiter likely formed farther from the Sun than it is today and migrated inward before eventually moving back out again. Saturn's migration was also significant. and the gravitational interactions between Jupiter and Saturn as they migrated may have been responsible for scattering bodies from the outer solar system, including the comets and asteroids that later bombarded the inner planets during a period called the Late Heavy Bombardment, about 4 billion years ago. These migrations also affected the formation of the terrestrial planets. If Jupiter had migrated too far inward, it might have scattered the material that was forming the inner planets, preventing Earth from ever forming. The fact that we exist suggests that Jupiter's inward migration was limited, possibly because Saturn's gravity pulled Jupiter back outward before it could disrupt the inner solar system too severely. Saturn's rings are another fascinating aspect of the planet that connects to the broader solar system history. The rings are not primordial. They didn't form when Saturn formed. Current evidence suggests they're much younger, perhaps only 100 to a few hundred million years old. They likely formed from the destruction of a small moon or a large comet that wandered too close to Saturn and was torn apart by tidal forces. When an object comes too close to a planet, the gravitational pull on the near side of the object is significantly stronger than the pull on the far side. If this difference, called a tidal force, exceeds the object's own gravity holding it together, the object gets pulled apart. The distance at which this happens is called the Roche limit, and it varies depending on the densities of the planet and the object. For Saturn, the Roche limit is inside the main ring system, which is why the rings exist where they do. The ring particles, mostly water ice ranging from tiny grains to house-sized boulders, orbit Saturn independently. They're constantly colliding with each other at low speeds, grinding each other down, creating a thin disk of material spread around Saturn's equator. The rings are remarkably thin relative to their extent, sometimes only tens of meters thick, despite stretching hundreds of thousands of kilometers across. But the rings are not stable forever. They're slowly being eroded by several processes. Ring material falls into Saturn's atmosphere, pulled down by the planet's magnetic field. Meteoroid impacts knock particles out of the rings and into space. Saturn's moons gravitationally perturb the rings, creating waves and gaps. Within another 100 million years or so, the rings will be mostly gone, dispersed or fallen into the planet, and Saturn will look much more like Jupiter, just another gas giant without the spectacular feature that makes it so distinctive. Saturn's moons are a solar system unto themselves. There are over 80 known moons, though many are tiny, irregular bodies only a few kilometers across, probably captured asteroids or comets. The largest moons are fascinating worlds in their own right. Titan, the second largest moon in the solar system, is bigger than the planet Mercury. It has a thick nitrogen atmosphere, thicker than Earth's, and liquid methane lakes on its surface. Titan is the only moon in the solar system with a substantial atmosphere, and it's one of the most Earth-like places we found, albeit at frigid temperatures of negative 180 degrees Celsius. The methane on Titan exists in a cycle similar to water's cycle on Earth. Methane evaporates from lakes, forms clouds, falls as rain, flows in rivers, and returns to the lakes. There are methane storms, methane clouds, methane fog. The chemistry happening in Titan's atmosphere and on its surface is complex, involving organic molecules being formed by ultraviolet light from the sun, breaking apart methane and nitrogen, creating compounds called tholins that give Titan's atmosphere its distinctive orange haze. Beneath Titan's icy crust, there's likely a subsurface ocean of liquid water, mixed with ammonia, kept liquid by tidal heating from Saturn and possibly by radioactive decay in Titan's rocky core. This ocean, if it exists, could potentially harbor life, though the extreme cold and the chemistry being very different from Earth's make it uncertain whether biology could emerge there. Another of Saturn's moons, Enceladus, has become one of the most exciting targets in the search for extraterrestrial life. Enceladus is small, only about 500 kilometers in diameter, but the Cassini spacecraft discovered something remarkable. Geysers of water vapor and organic compounds erupting from cracks near the South Pole. These geysers confirmed that Enceladus has a liquid water ocean beneath its icy surface, kept warm by tidal heating as Saturn's gravity flexes and kneads the Moon during its orbit. The water from this subsurface ocean sprays into space through the cracks, creating a faint ring around Saturn made of ice crystals from Enceladus. Cassini flew through these plumes and analyzed their composition, finding not just water, but also organic molecules, salts, and molecular hydrogen. The presence of hydrogen suggests there might be hydrothermal vents on the ocean floor, places where hot water from Enceladus's interior meets the cold ocean, creating chemical gradients that could provide energy for life. On Earth, hydrothermal vents host rich ecosystems based on geosynthesis rather than photosynthesis, deriving energy from chemical reactions rather than sunlight. Could similar ecosystems exist in Enceladus's ocean? We don't know, but it's one of the most compelling possibilities for finding life elsewhere in our solar system. Future missions might sample the plumes more thoroughly or even land on Enceladus and drill through the ice to directly access the ocean below. Saturn's system of moons and rings is a dynamic environment, constantly changing. Moons gravitationally interact with each other and with ring particles, creating complex orbital resonances. Some moons orbit at distances where their orbital period is a simple fraction of another moon's period, creating regular gravitational tugs that can amplify small effects over time. These resonances create gaps in the rings, waves in the ring material, and affect the orbits of the moons themselves. The study of Saturn and its moons has given us insights into planetary formation, atmospheric dynamics, exotic chemistry, and the possibility of life in unexpected places. But Saturn is also part of a larger story, the story of how our solar system formed from a cloud of gas and dust 4.5 billion years ago. That cloud, called the solar nebula, was part of the interstellar medium, the thin gas and dust spread between the stars in our galaxy. The material in the solar nebula came from previous generations of stars. When massive stars explode as supernova, they scatter their enriched material into space, including all the elements heavier than hydrogen and helium that were created in the star's cores, or in the explosions themselves. Our sun and solar system formed from such enriched material. The hydrogen and helium were primordial, created in the Big Bang, but the heavier elements, the carbon, oxygen, nitrogen, silicon, iron, and all the rest, were stellar products. This means that Saturn's rocky core, the icy materials in its satellites, and even the trace amounts of heavier elements in Saturn's atmosphere all came from stars that lived and died before our solar system existed. The process of solar system formation began when a region of the interstellar medium, perhaps already slightly denser than average, began to collapse under its own gravity. The trigger might have been a shock wave from a nearby supernova, compressing the cloud and initiating the collapse. Or it might have been spontaneous, a random fluctuation that grew until gravity took over. As the cloud collapsed, it began to spin faster, conserving angular momentum. The rotation caused the material to flatten into a disk, with most of the mass concentrated at the center where the sun would eventually form. The disk was hot near the center, heated by the release of gravitational potential energy as material fell inward, but cold in the outer regions far from the forming sun. Within the disk, solid particles began to condense. Close to the sun, only rocky and metallic materials could condense because it was too hot for ices. Farther out, beyond the frost line, water ice could condense as well, providing much more solid material. These particles stuck together when they collided, gradually growing from dust grains to pebbles to boulders to kilometer-sized planetesimals. The planetesimals continued to collide and merge, growing into planetary embryos and eventually into planets. In the inner solar system, this process created the terrestrial planets. In the outer solar system, it created the cores of the giant planets. Once Jupiter's and Saturn's cores reached about 10 Earth masses, they could capture gas from the nebula, growing rapidly into gas giants. The gas accretion phase lasted perhaps a few million years until the solar nebula was dispersed, probably by radiation and wind from the young sun. The planet's growth largely stopped at that point, though impacts continued for hundreds of millions of years afterward, bringing additional material and energy. The late heavy bombardment about 4 billion years ago may have delivered water to Earth and other inner planets, possibly making our world habitable. This narrative of solar system formation is supported by observations of other star systems. We've now discovered thousands of exoplanets, planets orbiting other stars, and we see planetary systems in various stages of formation. Young stars are surrounded by protoplanetary disks, just as our sun once was. Older stars have fully formed planetary systems, some similar to ours, others radically different. Many exoplanetary systems contain hot Jupiters, giant planets orbiting very close to their stars, with orbital periods of just a few days. These planets probably didn't form where we find them. Instead, they formed farther out and migrated inward, perhaps through interactions with the protoplanetary disk or with other planets. This shows that planetary migration is not unique to our solar system, but is a common feature of planetary system evolution. Other systems contain super-Earths, planets larger than Earth but smaller than Neptune, orbiting in the inner regions of their systems. Our solar system doesn't have any planets in this size range, which is interesting. Why not? Perhaps it's related to Jupiter's formation and migration history, which may have prevented a super-Earth from forming in the inner solar system. Or perhaps we're just seeing selection effects. Super-Earths are easier to detect than Earth-sized planets, so they appear common in our exoplanet surveys, even if they're not necessarily more common than solar systems like ours. The diversity of exoplanetary systems tells us that solar system formation doesn't always proceed the same way. Initial conditions matter. The mass and composition of the protoplanetary disk, the presence or absence of nearby stars, the timing of various processes, all these factors affect the final outcome. Our solar system is one result of this complex process, but it's not the only possible result or even necessarily the most common one. Studying Saturn in the context of exoplanets raises interesting questions. How common are ringed planets? We know Jupiter, Uranus, and Neptune all have rings, though none as spectacular as Saturn's. Do exoplanets have rings? We haven't detected any yet, but that's likely because rings would be very difficult to see at interstellar distances with current technology. Future telescopes might be able to detect rings around nearby exoplanets, which would tell us whether rings are a common feature of giant planets or something special about our solar system. What about moons like Titan and Enceladus? Do other giant planets have large moons with thick atmospheres or subsurface oceans? Again, we don't know because we can't yet detect exomoons. But it seems likely that many giant exoplanets have substantial moon systems, and some of those moons might be habitable, or at least interesting for astrobiology. This brings us to one of the most profound questions we can ask. Is there life elsewhere in the universe? We don't know if life exists anywhere beyond Earth, but the possibility is tantalizing. In our own solar system, the most promising places to look are not other planets, but moons. Enceladus with its subsurface ocean and hydrothermal activity, Titan with its complex organic chemistry, Europa, Jupiter's moon with its vast ocean beneath an icy shell, and perhaps others. If we find life on one of these moons, it would be one of the most significant discoveries in human history. It would tell us that life is not unique to Earth, that it can arise independently in different environments, that the universe might be teeming with biology, even if intelligent life is rare. It would also raise new questions. Is this life related to Earth life, perhaps seeded from Earth by meteorites? Or is it truly independent, a second genesis? How does it compare to Earth life biochemically? What can it tell us about the range of possible biologies? Even if we don't find life in our solar system, the search for life extends to exoplanets. Astronomers are looking for biosignatures in exoplanet atmospheres, gases like oxygen and methane, that might indicate biological activity. Finding such signatures wouldn't prove life exists, but it would make it more plausible and would justify more detailed investigation. The connection between Saturn and the search for life might not be obvious at first, but it's there. Saturn's moons are possible habitats. Understanding Saturn's atmospheric chemistry helps us interpret observations of exoplanets. Studying how giant planets form and evolve tells us what kinds of planetary systems might be hospitable to life. Everything is connected in astronomy and planetary science. Let's zoom out even further now, beyond the solar system to the galaxy itself. Our Sun is one of hundreds of billions of stars in the Milky Way galaxy. It's located in a spiral arm about halfway from the galactic center to the edge, in a relatively quiet region without many massive stars nearby. This has been important for Earth's habitability. Massive stars live short lives and explode as supernova, which would bathe nearby planets in harmful radiation. Our Sun's location in a calmer part of the galaxy has allowed life on Earth to evolve over billions of years without being sterilized by a nearby supernova or gamma-ray burst. The Sun orbits the galactic center once every 200 to 250 million years, a period called a galactic year. Saturn and all the other planets orbit with the Sun, bound to it by gravity. Since the solar system formed 4.5 billion years ago, we've completed about 20 galactic orbits. We're currently moving through space at about 230 kilometers per second, relative to the galactic center, though we don't feel this motion because everything in our vicinity is moving with us. As the solar system orbits the galaxy, it passes through different regions with different properties. Sometimes we're in a spiral arm where stars are forming, and massive young stars are common. Other times we're between spiral arms and quieter regions. Some scientists have speculated that these passages might affect Earth's climate or the rate of impacts from comets, possibly even influencing mass extinctions. But the evidence is weak, and the effects, if they exist at all, are subtle. The galaxy itself is a vast system, a disk of stars, gas, and dust about 100,000 light-years in diameter and a few thousand light-years thick. At the center is a supermassive black hole containing about 4 million times the mass of the Sun, surrounded by a dense cluster of stars orbiting at tremendous speeds. The spiral arms are regions of active star formation, where giant molecular clouds collapse to create new stars. Most of the galaxy's mass is not in stars, but in dark matter, an invisible substance that interacts only through gravity. Dark matter forms a vast halo extending far beyond the visible disk, and its gravity holds the galaxy together and shapes its rotation. We know dark matter exists because the galaxy rotates too fast for the visible matter alone to hold it together gravitationally, but we don't know what dark matter is made of. It remains one of the great mysteries of modern physics. The Milky Way is just one galaxy among billions in the observable universe. It's part of a small group called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller galaxies. Andromeda is the nearest large galaxy to us, about 2.5 million light-years away, and it's actually approaching us. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a single larger galaxy. Don't imagine this as a violent crash. Galaxies are mostly empty space, and when they merge, individual stars rarely collide. Instead, the galaxies pass through each other, their gravity distorting both, creating long tidal tails of stars pulled out by the interaction. Eventually, after multiple passes, they'll settle into a single elliptical galaxy, a smooth distribution of old stars without the spiral structure that characterizes both the Milky Way and Andromeda today. By the time this happens, Saturn and the other planets will still be orbiting the Sun, assuming nothing disrupts the solar system during the merger. The Sun will have evolved into a red giant, having exhausted the hydrogen in its core and expanded to perhaps 100 times its current size, possibly engulfing Mercury and Venus, and certainly making Earth uninhabitable. Saturn will be farther from this bloated Sun and less affected, though it might lose some of its atmosphere to the increased solar wind from the dying star. Eventually, in about 7 to 8 billion years, the Sun will shed its outer layers as a planetary nebula and collapse into a white dwarf, a dense remnant about the size of Earth containing about half the Sun's current mass. The outer planets, including Saturn, might survive this transition, orbiting the white dwarf in cold darkness as the stellar remnant slowly cools over trillions of years. This brings us to think about deep time, the vast stretches of billions of years over which the universe evolves. 4.5 billion years ago, when Saturn formed, the universe was already 9 billion years old. Stars had been forming and dying for billions of years before our solar system came into existence. The atoms in Saturn's core were forged in earlier stars, scattered into space by supernova explosions, recycled through multiple generations before being incorporated into the solar nebula. But before we leave Saturn entirely and drift into sleep, let's contemplate a few more connections. A few more threads that tie this magnificent ringed world to the deepest questions we can ask about existence itself. Think about the nature of time as it relates to Saturn. We measure Saturn's rotation period at about 10.5 hours, giving the planet a very short day. But what does this rotation mean in the broader cosmic context? Saturn has been rotating since it formed 4.5 billion years ago. In that time, it has completed roughly 4 trillion rotations. 4 trillion days on Saturn, while Earth has experienced only about 1.5 trillion days. This reminds us that time is not absolute. A day is just one rotation of a planet. A year is just one orbit around a star. These are local measurements, meaningful for creatures living on those worlds, but arbitrary from a cosmic perspective. An intelligent being living in Saturn's atmosphere, if such a thing were possible, would experience time very differently from us. Their day would be much shorter. Their year would be 29 Earth years long. The rhythm of their existence would be fundamentally different. Einstein's relativity tells us that time is even more flexible than this. Time passes at different rates depending on how fast you're moving and how deep you are in a gravitational field. On the surface of a neutron star where gravity is extreme, time passes noticeably slower than it does in interstellar space. Near the event horizon of a black hole, time dilation becomes so extreme that from an outside perspective, time appears to stop entirely for anything crossing the horizon. This means that the universe doesn't have a single universal clock ticking at the same rate everywhere. Time is local, personal, almost depending on your reference frame. When we say Saturn is 4.5 billion years old, we're measuring that time in Earth's reference frame, far from any extreme gravitational fields, and moving at relatively modest speeds through the galaxy. An observer in a different reference frame might measure a different elapsed time since Saturn's formation. And yet, despite this relativity of time, there are absolute aspects to the universe. The speed of light is the same for all observers, regardless of their motion. The laws of physics are the same everywhere. The fundamental constants like the gravitational constant, the charge of an electron, the mass of a proton, these appear to be the same throughout the observable universe and perhaps beyond. Why should this be? Why should the universe have laws at all? Why should those laws be mathematical, expressible in equations that we can write down and solve? These are deep questions that science can describe, but perhaps not fully answer. We can discover what the laws are, but not why they exist or why they take the particular form they do. Some physicists speculate that the laws of physics might be different in other universes, if such things exist. In the multiverse hypothesis, our universe is just one bubble in a vast foam of universes, each with potentially different physical laws, different constants, different dimensionality even. Most of these universes would be sterile, unable to support complexity or life. We find ourselves in one of the rare universes where the constants are tuned to allow for stars, planets, chemistry, and biology. This is called the anthropic principle in its strong form. We observe the universe to have properties compatible with our existence because if it didn't, we wouldn't be here to observe it. It's a controversial idea because it seems to give up on finding deeper explanations for why our universe is the way it is. Instead of explaining the fine-tuning of constants, it just says we couldn't exist in a universe with different constants. So of course we find ourselves in one of the rare universes where the constants Allow for complexity. Whether you find this satisfying or not depends on your philosophical inclinations, but it raises profound questions about the nature of existence and our place in the cosmos. Are we extraordinarily lucky to exist in a universe with the right properties? Or is our existence inevitable in a multiverse where all possible universes exist? Or is there some deeper principle we haven't discovered that explains why the constants must have the values they do? These questions go beyond physics into metaphysics, into philosophy, into the realm where science touches on ancient questions about why there is something rather than nothing, about whether existence requires explanation or is simply a brute fact. We may never have complete answers to these questions, but asking them is part of what makes us human, part of what makes consciousness valuable. And this brings us back to consciousness itself, perhaps the deepest mystery of all. You are conscious right now, aware of yourself, aware of these words, aware of the act of being aware. This subjective experience, this inner mental life, is the most immediate and certain fact of your existence. Descartes was right. You think, therefore you are. But what is consciousness? How does it arise from physical processes in the brain? Why does the universe contain not just matter and energy, but also subjective experience? These questions have puzzled philosophers for millennia and continue to challenge neuroscientists and physicists today. Some think consciousness is an emergent property of complex information processing, that it arises naturally when a system becomes sophisticated enough. In this view, there's nothing mysterious about consciousness. It's just what complex computation feels like from the inside. But this doesn't really explain why there should be any feeling from the inside at all. Why should information processing be accompanied by subjective experience? Others think consciousness might be more fundamental, perhaps a basic feature of the universe like space and time and matter. This view, called panpsychism, suggests that all matter has some rudimentary form of consciousness, or proto-consciousness, and what we experience as consciousness is what emerges when matter organizes itself into sufficiently complex structures like brains. But this raises its own questions. What would it mean for an electron to have proto-consciousness? How does proto-consciousness combine to create the rich consciousness we experience? Still, others think consciousness might be related to quantum mechanics in some deep way. Quantum mechanics deals with probabilities and measurements, and some interpretations involve consciousness in the collapse of the wave function. Perhaps consciousness and quantum mechanics are intimately connected. Perhaps the ability to observe and collapse quantum states is what consciousness fundamentally is. But most physicists are skeptical of these quantum consciousness theories, and the evidence for them is weak. We simply don't know what consciousness is or how it arises. It remains one of the hardest problems in all of science, perhaps the hardest problem. And yet, despite not understanding consciousness, we can study it, describe it, even manipulate it to some extent with drugs or brain stimulation or meditation practices. The existence of consciousness also raises questions about artificial intelligence. Can machines be conscious? If we build a computer sophisticated enough, will it have subjective experiences? Or is biological consciousness special, tied to the particular physics and chemistry of neurons in ways that can't be replicated in silicon? These are not just academic questions. As artificial intelligence becomes more sophisticated, we'll need to grapple with these issues. How do we know if an AI system is conscious? What moral status should we give it if it is? These are questions that science fiction has explored for decades, but they're becoming practical concerns as AI capabilities advance. And if consciousness can exist in different substrates, not just biological brains but also in sufficiently advanced computers, then perhaps consciousness is more common in the universe than we think. Perhaps there are conscious as created by alien civilizations. Perhaps consciousness can exist in forms we haven't imagined, in the organization of plasma, in stellar atmospheres, or in quantum states of exotic matter. This is wild speculation, but it's the kind of speculation that becomes meaningful when we realize how little we understand about consciousness. Returning to Saturn one more time, we can ask, could there be consciousness associated with Saturn in any way? Obviously not in the way we're conscious, because Saturn doesn't have a brain or nervous system. But what about the complex dynamics of its atmosphere, the organized circulation patterns, the storm systems that persist for years? Is there any sense in which these organized patterns constitute a kind of information processing that might be associated with some form of proto-consciousness? Almost certainly not, at least not in any meaningful sense. But the question itself is interesting because it highlights how we don't really know where to draw the line between conscious and non-conscious systems. We're confident that we are conscious, pretty confident that other humans and most animals are conscious, less sure about insects, and even less sure about plants or bacteria. And we have no idea whether consciousness could exist in non-biological systems or in systems very different from terrestrial life. These questions about consciousness connect to questions about the meaning and purpose of existence. If consciousness is rare and precious, if we're alone or nearly alone in the universe, then perhaps that gives us special significance and special responsibility. We become the universe's way of knowing itself, the only eyes through which the cosmos can observe its own existence. But if consciousness is common, if the universe is teeming with awareness in forms we can't yet imagine, then we're just one instance among countless others, no more significant than any other conscious being. This is humbling but also comforting in a way. We're not alone. We're part of a great community of consciousness scattered across the cosmos. Which view is correct? We don't know. The search for extraterrestrial intelligence continues, listening for signals, looking for signs of technology or biology on distant worlds. So far we've found nothing, but the search has barely begun. We've only examined a tiny fraction of possible targets, and we're only just beginning to have the technology to detect biosignatures on exoplanets. The Fermi paradox asks, if intelligent life is common, where is everyone? Why haven't we detected any signs of alien civilizations despite the vastness and age of the universe? Many solutions have been proposed. Perhaps life is rare. Perhaps intelligence is rare. Perhaps technological civilizations tend to destroy themselves soon after developing advanced technology. Perhaps they're out there but too far away or communicating in ways we haven't thought to look for. Perhaps they're deliberately hiding from us, or we're inside some kind of cosmic zoo where we're observed but not contacted. Each solution to the Fermi paradox paints a different picture of our cosmic situation. If we're alone, that's profound and perhaps terrifying. If we're common but isolated by vast distances, that's poignant. If civilizations tend to self-destruct, that's a warning. If aliens are hiding or we're being observed, that raises whole new sets of questions about cosmic ethics and the rules governing contact between civilizations at different levels of development. We may get answers to some of these questions in the coming decades or centuries as our technology improves and our search intensifies. Or we may never know for certain. The universe is vast, and even if life is common, the distances between stars are so great that contact might be effectively impossible, even if civilizations wanted to communicate. Think about the scale involved. The nearest star to our Sun is Proxima Centauri, about 4 light-years away. That means light takes 4 years to travel from there to here. If we sent a signal to Proxima Centauri today, a reply would take at least 8 years to come back. And Proxima Centauri is our nearest neighbor. Most stars in the galaxy are thousands or tens of thousands of light-years away. A conversation with a civilization orbiting one of those stars would take millennia for each exchange of messages. And that's assuming communication at the speed of light, the cosmic speed limit. If we want to actually visit other star systems, we face even greater challenges. With current technology, it would take tens of thousands of years to reach even the nearest stars. We'd need breakthroughs in propulsion technology, perhaps fusion rockets or antimatter engines, or something even more exotic to make interstellar travel feasible on human timescales. Some scientists speculate about technologies like warp drives that could circumvent the light speed limit by warping space-time itself, or wormholes that could connect distant points in space. These are theoretically possible according to general relativity, but they require exotic matter with negative energy density, and it's not clear whether such matter can exist or how we could manipulate it if it does. So perhaps we're stuck in our solar system for the foreseeable future, limited to exploring our cosmic neighborhood with robotic probes and telescopes. This isn't a small domain. Our solar system extends far beyond the planets. The Kuiper Belt, a region of icy bodies beyond Neptune's orbit, stretches out to perhaps 50 astronomical units from the Sun. The Oort cloud, a spherical shell of comets surrounding the solar system, might extend halfway to the nearest star. There's plenty to explore right here in our solar system. We've only sent spacecraft to all the planets relatively recently. Many moons remain unexplored. Asteroids and comets contain clues about the early solar system. The outer reaches of the Kuiper Belt and Oort cloud are virtually unknown. We could spend centuries exploring our solar system thoroughly and still find new discoveries. And perhaps that's enough. Perhaps the meaning of existence isn't about spreading across the galaxy or finding aliens. Perhaps it's about understanding our own world, our own solar system, our own consciousness. Perhaps it's about creating meaning here and now rather than searching for cosmic purpose. This is a very human perspective, of course. We seek meaning and purpose because we're conscious beings who can ask these questions. But the universe itself is indifferent to our questions. Saturn's storms rage whether we observe them or not, whether we find meaning in them or not. The universe simply is following physical laws, evolving according to deterministic and probabilistic processes, creating complexity and structure, and sometimes on rare worlds under rare conditions, creating life and consciousness. We are part of that process, temporary patterns in the flow of matter and energy, brief flowers of consciousness blooming in a vast and ancient cosmos. We arose from the universe, from stardust and chemistry and evolution, and eventually will return to it, our atoms dispersing, contributing to future generations of stars and planets and perhaps new forms of life. This cosmic perspective can be liberating. Our problems and anxieties, our daily concerns, they're real and important on a human scale, but they're tiny and temporary on a cosmic scale. The universe has existed for 13.8 billion years and will continue for trillions more. Human history is a few thousand years. Your individual life is measured in decades. These are meaningful spans of time for you, but they're infinitesimal compared to cosmic timescales. This doesn't make your life meaningless. If anything, it makes it more precious. You have this brief window of consciousness, this short time to experience existence, to love and learn and create and wonder. The universe gave you this gift, assembled atoms in just the right way to create awareness, and you get to experience it, to be part of the universe knowing itself. Saturn has been orbiting the Sun for 4.5 billion years, churning with storms, radiating heat, maintaining its rings and moons. It will continue for billions more. But you get to know about it. You get to contemplate its existence, to understand its structure and formation, to appreciate its beauty. This is a remarkable privilege, made possible by the evolution of consciousness on a small blue planet in the outer suburbs of an ordinary galaxy. And so we come full circle, from the storms in Saturn's atmosphere to the depths of planetary structure, to the formation of the solar system, to the nature of stars and galaxies, to the origins of the universe, to the mystery of consciousness and the search for meaning. All of it connects. All of it is part of one grand cosmic story, and you are part of that story, a character in the narrative of the universe, brief but significant, temporary but meaningful. The storms on Saturn continue at this very moment, lightning flashing, winds howling, clouds churning. They've been doing this for billions of years and will continue for billions more. And now, having contemplated these storms and everything they connect to, having traced threads from Saturn to the cosmos and back to consciousness itself, it's finally time to rest. But before sleep takes you completely, let's spend a few more moments contemplating the physical processes that make Saturn and all the other wonders of the universe possible. Let's think about the fundamental forces and particles that underlie everything we've discussed. All of physical reality, from the smallest subatomic particle to the largest galaxy supercluster, is governed by just 4 fundamental forces. Gravity, the weakest but longest range force, shapes the cosmos on large scales, pulling matter together into stars, planets, and galaxies. Electromagnetism governs the interactions between charged particles, holding atoms together, creating light, powering all of chemistry and biology. The strong nuclear force binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion between positively charged protons. And the weak nuclear force is responsible for certain types of radioactive decay and plays a crucial role in nuclear fusion in stars. These 4 forces seem very different from each other, but physicists have discovered deep connections between them. In the 1960s and 70s, theoretical work showed that electromagnetism and the weak force are actually 2 aspects of a single electroweak force, unified at high energies. At the enormous temperatures that existed shortly after the Big Bang, these 2 forces were indistinguishable. Only as the universe cooled and underwent phase transitions did they separate into the distinct forces we observe today. This unification of forces is one of the great triumphs of 20th century physics. and it hints that the other forces might be unifiable as well. Grand unified theories attempt to show that the strong force is also unified with the electroweak force at even higher energies that existed in the first fraction of a second after the Big Bang. And theories of everything, like string theory, attempt to include gravity as well, showing that all four forces are ultimately aspects of a single unified force that operated when the universe was incredibly young, incredibly hot, and incredibly dense. String theory is particularly interesting because it's not just a theory of forces, but a theory of everything. It proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings, perhaps 10 to the minus 35 meters long, far smaller than atoms or even quarks. Different vibration patterns of these strings correspond to different particles. An electron is a string vibrating one way, a quark is a string vibrating another way, a photon is a string vibrating yet another way. String theory is mathematically beautiful and elegant, but it comes with strange requirements. For the mathematics to work, the theory requires extra dimensions beyond the 3 spatial dimensions we experience. Depending on the version, string theory needs 9 or 10 spatial dimensions plus time. Where are these extra dimensions? The theory says they're compactified, curled up into tiny structures too small to detect, present at every point in space but invisible because they're so minuscule. This sounds bizarre, but it's actually not that different from other situations in physics. Imagine an ant walking on a tightrope. From the ant's perspective, the rope has length but no width. It's effectively one-dimensional. But from our perspective, we can see that the rope has a small but non-zero thickness, a second dimension that exists but is too small for the ant to notice. String theory suggests our universe might be like that rope from the ant's perspective. We perceive 3 spatial dimensions, but there might be additional dimensions curled up too small for us to detect. If string theory is correct, it would revolutionize our understanding of reality. It would explain not just the forces, but also why particles have the masses and charges they do, why there are 3 generations of quarks and leptons, why the universe has the properties it does. It might even explain the Big Bang itself, showing how our universe arose from quantum fluctuations in a higher dimensional space. But string theory has a problem. It's very difficult to test experimentally. The energies required to directly observe strings or extra dimensions are far beyond what we can achieve with particle accelerators, perhaps far beyond what we could ever achieve. This has led to criticism that string theory is more mathematics than physics, untestable, and therefore unscientific. Proponents argue that while we can't test string theory directly, we can test its predictions and look for indirect evidence. The theory makes predictions about the early universe that might be visible in the cosmic microwave background. It predicts certain patterns in particle physics that could be detected at colliders. It provides a framework for understanding black holes and quantum gravity. Even if we can't test the theory definitively, we can constrain it and see if it matches observations. Whether string theory is ultimately correct or not, the search for it represents something profound about human consciousness and curiosity. We want to understand reality at its deepest level. We're not satisfied with knowing that 4 forces exist. We want to know why they exist and whether they're connected. We're not content with describing how the universe behaves. We want to understand why it behaves that way. This drive to understand, this capacity for abstract thought and mathematical reasoning, is one of the most remarkable features of consciousness. We can think about things we can't directly observe, like extra dimensions, or the interior of black holes, or the first moments after the Big Bang. We can create mental models, mathematical frameworks, thought experiments that let us explore realms of reality far beyond our immediate sensory experience. And sometimes, remarkably, these abstract mathematical ideas turn out to describe physical reality. Einstein developed general relativity through pure thought, using mathematics to explore what gravity must be like if it's connected to the geometry of space-time. His equations predicted things like black holes and gravitational waves and the expansion of the universe, all of which were later confirmed by observation. The mathematics guided us to truths about nature that we never would have discovered through observation alone. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, is deeply mysterious. Why should the universe be mathematical? Why should physical laws be expressible in equations? Why should abstract mathematical structures invented by humans correspond to real features of nature? We don't have good answers to these questions, but the fact remains that mathematics works extraordinarily well for understanding and predicting physical phenomena. Perhaps the universe is mathematical at its core. Perhaps reality is fundamentally made of mathematical structures and relationships, rather than some underlying substance. This is a philosophical position called mathematical Platonism, or mathematical universe hypothesis, and it suggests that physical existence is a particular mathematical structure, and everything that exists is part of that structure. Or perhaps mathematics is just the language our minds use to describe patterns we observe in nature, and the success of mathematics reflects the fact that nature has patterns and our minds evolved to detect patterns. In this view, mathematics is a human creation, a tool we've developed that happens to be very effective for describing the universe, because the universe has regularities that mathematical descriptions can capture. Whichever view is correct, the relationship between mathematics and physical reality is profound and puzzling. And it's through mathematics that we understand Saturn and its storms, that we can calculate atmospheric dynamics and interior structure, that we can predict planetary orbits and stellar evolution. Mathematics lets us peer into realms we can never visit and understand processes we can never observe directly. Think about what this means. You, lying here now, can understand Saturn's interior, can know that metallic hydrogen exists there, even though no human has ever seen metallic hydrogen, and probably never will. You can know that helium rain falls deep within the planet, even though you'll never observe a single droplet. You can comprehend the processes that formed Saturn 4.5 billion years ago, even though you weren't there and no one was. This is the power of mathematical reasoning combined with physical observation. And this power extends far beyond Saturn. We can understand the Big Bang, an event that happened 13.8 billion years ago, long before Earth existed, long before any observer existed. We can know what the universe was like in its first seconds, when it was a hot, dense plasma of fundamental particles. We can trace the evolution of matter and energy from that early state to the present day, explaining how simple hydrogen and helium evolved into stars and galaxies, and eventually into planets and life. We can even peer into the future, using the laws of physics to predict what will happen billions of years from now. We know the sun will eventually exhaust its hydrogen fuel and expand into a red giant. We know the Milky Way and Andromeda will collide and merge. We know, if our current understanding is correct, that the universe will continue expanding forever, eventually becoming cold and dark and empty. These are knowledge claims about events billions of years in the future, yet we can make them with reasonable confidence because we understand the underlying physics. This is both empowering and humbling. Empowering because it shows how far human understanding has come, how much we've learned about the universe through observation, experimentation, and reason. Humbling because it reveals our cosmic insignificance, the tiny role we play in a vast universe that existed long before us and will continue long after we're gone. But perhaps insignificance is the wrong word. Size and duration don't determine significance. A human life might be brief compared to the age of the universe, but it contains experiences, relationships, thoughts, and feelings that are meaningful regardless of their cosmic scale. Consciousness and understanding are themselves remarkable, precious even, regardless of how much space or time they occupy. You are a small part of a large cosmos, yes, but you're a part that can understand the whole. You're matter that has organized itself to contemplate matter, atoms arranged in such a way that they can wonder about atoms. The universe has created in you the capacity to know itself. That's extraordinary, no matter how you measure significance. And this capacity for understanding brings with it responsibility. We know now how fragile planetary habitability is, how special Earth's conditions are, how easily they could be disrupted. We know we're changing our planet's climate and ecosystems in ways that could make Earth less habitable for ourselves and countless other species. This knowledge should motivate us to be better stewards of our world. We also know, or at least suspect, that we might be alone or nearly alone in the universe, that consciousness might be rare and precious. This should make us value not just human life, but all life, all consciousness, wherever and however it manifests. If we're the only minds in the galaxy capable of understanding the cosmos, that's a profound privilege and a profound responsibility. These ethical considerations emerge from cosmic understanding. When you grasp how old the universe is, how vast it is, how special the conditions for life are, it changes how you see yourself and your place in existence. It can make daily concerns seem trivial, but it can also make life itself seem more precious. It can inspire wonder, humility, and a sense of connection to something larger than yourself. This is perhaps one of the most valuable things we gain from contemplating Saturn and storms and the cosmos. Perspective. A reminder that we're part of something vast and ancient, that our lives are brief but meaningful, that consciousness and understanding are gifts to be cherished, that the universe is full of wonders waiting to be discovered. And with that perspective comes a kind of peace. Whatever troubles you face, whatever anxieties plague your mind, they're real and important to you, but they're also temporary and small against the backdrop of cosmic time and space. The universe will continue, the stars will keep burning, the galaxies will keep evolving, and within that vast, patient cosmos you have this moment, this consciousness, this opportunity to experience existence. Let's take one last journey through the implications of everything we've contemplated tonight. We began with storms on Saturn, tangible physical phenomena governed by fluid dynamics and thermodynamics. From there, we descended through atmospheric layers into exotic states of matter, metallic hydrogen and superionic ices existing under pressures and temperatures we can barely imagine. We traced Saturn's origins back to the formation of the solar system 4.5 billion years ago, understanding how this massive world grew from dust and ice and gas in the disk surrounding the young sun. We expanded our view to see Saturn as one member of a family of planets, comparing it to Jupiter and the ice giants, understanding how planetary migration shaped the solar system we see today. We looked at Saturn's moons and rings, discovering worlds like Titan with its thick atmosphere and methane lakes, and Enceladus with its subsurface ocean and geysers spraying water into space. These are places where life might potentially exist, alien ecosystems unlike anything on Earth, reminders that the universe might be full of biology in unexpected forms and locations. Then we zoomed out further to see our solar system as part of the Milky Way galaxy, one star system among hundreds of billions, orbiting the galactic center over hundreds of millions of years. We considered other planetary systems, the thousands of exoplanets discovered around other stars, recognizing that giant worlds like Saturn are probably common throughout the galaxy. We contemplated even larger scales, the universe itself, its origin in the Big Bang, its evolution over 13.8 billion years, its ultimate fate in the distant future. We touched on dark matter and dark energy, mysterious components that make up most of the universe but remain poorly understood. We discussed the possibility of multiverses, of other universes with different laws of physics, questioning whether our universe is unique or one among countless others. Before we finally surrender to sleep, let's explore just a bit further into some of the most fascinating questions that emerge from our contemplation of Saturn and the cosmos. These are questions that have no definitive answers yet, mysteries that remain at the frontier of human understanding, puzzles that future generations might solve or might find are unanswerable. Consider first the question of quantum gravity, the missing piece in our understanding of fundamental physics. We have quantum mechanics, which beautifully describes the behavior of particles and forces at microscopic scales. We have general relativity, which elegantly describes gravity and the large-scale structure of space-time. But these two theories are incompatible with each other in important ways. Quantum mechanics treats time as absolute and space as a fixed background. General relativity says time and space are dynamic and intertwined, curved by the presence of mass and energy. At most scales, this incompatibility doesn't matter. Quantum mechanics works perfectly for atoms and molecules and particle physics, where gravitational effects are negligible. General relativity works perfectly for planets and stars and galaxies, where quantum effects average out to insignificance. But there are places where both theories should be important. In black holes, where quantum effects should matter near the singularity, and in the very early universe, when all of existence was compressed into a quantum scale region. To understand these extreme situations, we need a theory of quantum gravity that successfully merges quantum mechanics with general relativity. String theory is one attempt at this. Loop quantum gravity is another. But we don't yet have a confirmed theory of quantum gravity, and without it, there are fundamental limits to our understanding. What happens at the center of a black hole? We don't know. Does the singularity really exist, or is it smoothed out by quantum effects? We don't know. What happened in the very first instant after the Big Bang? before cosmic inflation started. We don't know. How does space-time itself behave at the smallest scales? We don't know. These are not idle philosophical questions. They're concrete gaps in our scientific knowledge, places where our best theories fail to give answers. And this brings us to one of the deepest questions in all of science. Is the universe fundamentally deterministic or fundamentally probabilistic? Classical physics, including general relativity, is deterministic. If you know the exact state of a system at one time, and you know the laws of physics, you can in principle calculate its exact state at any other time. The future is determined by the past in a completely predictable way. But quantum mechanics introduces fundamental uncertainty. At the quantum level, outcomes are probabilistic. You can calculate the probability of finding an electron in a particular location, but you can't predict exactly where it will be. When a radioactive atom decays, there's no way to know exactly when it will happen. You can only calculate the half-life, the time by which half of a collection of such atoms will have decayed. This quantum randomness seems to be fundamental, not just a result of ignorance or incomplete information. Einstein famously objected to this, saying God does not play dice with the universe. He thought quantum mechanics must be incomplete, that there must be hidden variables determining the outcomes of quantum measurements. But experiments testing Bell's inequality have shown that if hidden variables exist, they would have to be non-local, affecting things instantaneously across space, which seems as problematic as accepting quantum randomness. So we're left with a universe that appears to be fundamentally probabilistic at its base, even if it's largely deterministic at macroscopic scales. This has profound implications for free will, causality, and the nature of time. If the future is not completely determined by the past, if there's genuine randomness built into reality, then the universe is genuinely open, genuinely creative, producing outcomes that couldn't have been predicted even in principle. Or perhaps the many worlds interpretation of quantum mechanics is correct, and every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. In this view, there's no randomness. Everything that can happen does happen, just in different branches of reality. The universe is deterministic at the level of the wave function, but from our perspective within one branch, it appears probabilistic because we can only see our branch, not all the others. These questions about determinism and probability connect to questions about time itself. Is time real and flowing, or is it an illusion? Does the present moment have special status, or is it just a particular point in space-time with no fundamental distinction from past or future? Is time travel possible, or does causality forbid it? Einstein's relativity treats time as a dimension similar to the three spatial dimensions, all woven together into space-time. In this view, past, present, and future all exist equally, and the flow of time is just a subjective feature of consciousness, not a fundamental aspect of reality. This is called the block universe view, and it suggests that everything that has happened or will happen exists eternally in the four-dimensional structure of space-time. But this view conflicts with our experience of time as flowing, of the present as special, of the past as fixed, and the future as open. And it's hard to reconcile with quantum mechanics, which seems to require a flowing time during which probabilities evolve and measurements cause outcomes to become actual. Some physicists think time might be emergent rather than fundamental, arising from more basic processes. In this view, the fundamental laws of physics might be timeless, and what we experience as time emerges from the evolution of entropy, or from quantum entanglement, or from some other underlying dynamics. This is speculative and controversial, but it's an active area of research in quantum gravity and foundations of physics. These deep questions about time, determinism, and quantum mechanics might seem abstract and disconnected from Saturn and its storms, but they're not. The storms on Saturn evolve according to physical laws that are ultimately quantum mechanical, even if quantum effects average out at the scales of atmospheric dynamics. The formation of Saturn billions of years ago involved quantum processes during nucleosynthesis in stars and during the chemical reactions that built complex molecules in the protoplanetary disk. Everything is connected, from the most practical and observable phenomena to the deepest and most abstract theoretical questions. You can't fully understand Saturn without understanding quantum mechanics, and you can't fully understand quantum mechanics without grappling with its philosophical implications. Science is not just a collection of facts, but a web of interconnected ideas, theories and questions, some answered and some still open. And perhaps some questions will always remain open. Perhaps there are fundamental limits to what we can know. Gödel's incompleteness theorems show that in any formal mathematical system complex enough to describe arithmetic, there are true statements that can't be proven within that system. This doesn't tell us directly about physics, but it suggests that completeness might be impossible, that there might always be questions we can ask that our theories can't answer. Similarly, there might be aspects of reality that are fundamentally unobservable. The interior of black holes, if information truly can't escape, might be forever hidden from us. The very early universe, before the first fraction of a second, might be impossible to probe because all information from that era has been erased by subsequent cosmic evolution. Other universes, if they exist, might be forever beyond our reach, detectable only indirectly, if at all. This possibility of fundamental limits to knowledge is both frustrating and liberating. Frustrating because it means there might be questions we'll never answer, truth we'll never know. Liberating because it means mystery will always remain, that the universe will always have depths to explore, that wonder will never be exhausted. Think about how much we've learned already. Ancients looked at the night sky and saw lights whose nature they could only guess at. Now we know what stars are, how they work, how they're born and live and die. We've stood on the moon, sent probes to every planet, observed galaxies billions of light years away. We've discovered quantum mechanics and relativity. We've measured the age of the universe and mapped its large-scale structure. We've found thousands of planets around other stars and detected gravitational waves from colliding black holes. This progress is extraordinary, achieved in just a few centuries of scientific investigation. But it hasn't exhausted mystery. If anything, every answer raises new questions. We know more than ever before, and we're more aware than ever of how much we don't know. The horizon of mystery keeps receding as we approach it, revealing new vistas of questions beyond. This is part of what makes science exciting and worthwhile. If we knew everything, if there were no questions left, science would be finished, complete, a closed book. But the book stays open, and probably always will. There will always be new things to discover, new questions to ask, new mysteries to contemplate. And this extends beyond science into philosophy and ethics and meaning. As we learn more about the universe, we have to reconsider our place in it, our values, our purposes. The discovery that Earth is not the center of the universe challenged ancient worldviews. The discovery of evolution challenged ideas about human uniqueness. The possibility of life elsewhere challenges ideas about our cosmic significance. Each scientific advance forces us to update not just our factual knowledge, but our philosophical frameworks. We have to integrate new discoveries into our understanding of what it means to be human, what consciousness is, what matters in life. Science and philosophy are not separate domains, but complementary approaches to understanding reality and our place in it. Consider the ethical implications of some recent and potential future discoveries. If we find microbial life on Mars or Enceladus, how should we treat it? Does it have moral value? Should we avoid contaminating it with Earth life? Should we protect it even if doing so limits our ability to study or exploit those worlds? These aren't just scientific questions, but ethical ones, requiring value judgments about what matters and why. If we eventually develop advanced artificial intelligence that appears to be conscious, how should we treat it? What rights should it have? Is it ethical to turn off or delete an AI if it's genuinely conscious? These questions will become increasingly pressing as AI capabilities advance, and science alone can't answer them. We need philosophical reasoning about consciousness, moral status, and the nature of ethical obligations. If we make contact with extraterrestrial intelligence, how should we respond? Should we try to communicate? What should we say? What are the risks and benefits of revealing our existence? These questions, explored endlessly in science fiction, might become practical concerns if we ever detect signals from an alien civilization, or if such a civilization finds us. All these ethical questions emerge from scientific discoveries and possibilities. As our knowledge expands, our moral universe expands with it. We have to consider entities and scenarios that previous generations never imagined. This is challenging but also enriching, forcing us to think deeply about what we value and why. And perhaps one of the most valuable things we can value is understanding itself. Curiosity, the drive to learn and explore and contemplate. This is part of what makes consciousness valuable. We don't just survive and reproduce. We wonder and question and seek to understand. We create art and music and literature. We build civilizations and technologies. We look at Saturn through telescopes and send spacecraft to orbit it and study it in detail. We're not content with simple existence. We want to understand existence. This drive to understand is quintessentially human, though perhaps not uniquely so. Other animals show curiosity and playfulness and problem-solving abilities. Primates use tools. Dolphins and crows solve puzzles. Elephants show signs of self-awareness. The capacity for understanding might exist in various degrees across the animal kingdom, with humans at one extreme, but not fundamentally different in kind from other intelligent species. And if consciousness and intelligence exist elsewhere in the universe, those beings probably share this stand, even if they approach it differently. Any species that develops technology has to understand physics at some level. Any civilization that studies the stars has to develop mathematics and astronomy. The specific forms might differ, but the underlying project, understanding reality through systematic observation and reasoning, might be universal among technological species. This suggests that science is not just a human endeavor, but potentially a cosmic one, a general method that any intelligence might use to comprehend the universe it finds itself in. The laws of physics are the same everywhere, and any intelligence studying those laws should eventually discover similar truths about how reality works, even if they describe those truths in different languages or mathematical frameworks. This universality of science is both humbling and empowering. Humbling because it means human science is not special or unique, just one instance of a more general process. Empowering because it means our discoveries are not arbitrary or culturally dependent, but reflect genuine features of reality that any intelligence could discover. When we say that Saturn's atmosphere contains ammonia clouds and water clouds and ammonium hydrosulfide clouds, we're making claims about objective reality, claims that any intelligence studying Saturn would eventually discover. The specific words might differ, the conceptual frameworks might vary, but the underlying facts are universal. This is what makes science work, what makes scientific knowledge cumulative and progressive. And it's what makes contemplating Saturn meaningful. We're not just making up stories or projecting human concerns onto an indifferent universe. We're discovering real facts about a real world, understanding actual processes governed by actual laws. Saturn really does have storms. Those storms really are powered by internal heat. The internal structure really does include metallic hydrogen. These are truths about reality, and finding them, understanding them, contemplating them. This is a genuine achievement, a real contribution to the cosmic story of consciousness, trying to understand the universe it emerged from. So as you lie here on the edge of sleep, having journeyed from Saturn's storms to the deepest questions of physics and philosophy, recognize what you've done. You've exercised your consciousness, your capacity for abstract thought and understanding. You've connected with a long human tradition of curiosity and discovery. You've touched truths about reality that are universal and eternal, facts about Saturn that were true long before humans existed and will remain true long after we're gone. This is a remarkable thing, this ability to know truths that transcend your individual existence. The knowledge that Saturn has storms doesn't depend on you. It's not personal or subjective. It's a fact about the cosmos, and you've grasped that fact, made it part of your understanding. In doing so, you've participated in the universe's grand project of self-understanding, become one node in the network of consciousness through which reality contemplates itself. And now, having participated, having wondered and learned and understood, it's time to rest. Knowledge is valuable, but so is sleep. Understanding is important, but so is renewal. You've done enough for tonight. You've thought enough, contemplated enough, connected enough. Now let it all go. Release these ideas into the quiet darkness. Let them settle into your unconscious mind while you sleep, perhaps to re-emerge later as inspiration or insight, or simply as a deeper appreciation for the cosmos. The universe doesn't stop for sleep. Right now, as you prepare to drift into unconsciousness, Saturn's storms continue raging 1.5 billion kilometers away. Lightning flashes through ammonia clouds. Winds howl at hundreds of meters per second. Convection cells rise and fall in the deep atmosphere. Metallic hydrogen flows in the interior, generating magnetic fields. The planet radiates heat into space, heat that has been flowing outward from the core for 4.5 billion years. And Saturn is not alone in its perpetual activity. On Jupiter, the Great Red Spot continues its centuries-long rotation, a storm larger than Earth that has been raging since at least the 1600s when it was first observed. On Titan, methane rain falls from orange skies onto hydrocarbon seas. On Enceladus, geysers spray water from subsurface oceans into the vacuum of space. Throughout the solar system, throughout the galaxy, throughout the universe, processes continue, phenomena occur, matter and energy flow and transform according to eternal physical laws. Before we take that final step into sleep, let's spend just a little more time contemplating one of the most profound aspects of our exploration tonight. The sheer fact that understanding is possible, that we can know things about Saturn, about the universe, about reality itself. This is not something to take for granted. It's actually quite mysterious when you think about it deeply. Why should the human brain, evolved on the plains of Africa to help our ancestors survive and reproduce, be capable of understanding quantum mechanics or general relativity or the internal structure of gas giant planets? Natural selection favored brains that could recognize patterns in their immediate environment, remember where food sources were, predict the behavior of predators and prey, cooperate with other members of their group. It didn't favor brains that could solve differential equations, or grasp the concept of space-time curvature, or contemplate the origin of the universe. And yet we can do these things. Our brains, shaped by evolution for practical survival tasks, turn out to have capacities far beyond what was needed for survival. We can do abstract mathematics. We can reason about things we've never directly experienced. We can build telescopes and particle accelerators and space probes to extend our senses far beyond their natural limits. We can use these tools to discover truths about reality that are completely disconnected from everyday survival concerns. This is what some philosophers call the unreasonable effectiveness of human reason. Our rational faculties work not just for practical, everyday tasks, but also for discovering deep truths about the universe. Why should this be? One possibility is that abstract reasoning abilities emerged as a byproduct of other capacities that were selected for. Perhaps the ability to plan ahead, to imagine scenarios that haven't happened yet, to reason about cause and effect. These practical abilities required cognitive machinery that could also be used for abstract thought about mathematics and physics. Or perhaps there's something more profound going on. Perhaps the universe is structured in such a way that intelligence inevitably develops the capacity to understand it. Perhaps mathematics and logic are not arbitrary human inventions, but reflect actual structure in reality, and brains that evolved to navigate reality would naturally develop some grasp of that structure. This would explain why mathematics is so effective in physics, why equations we write down describe natural phenomena so accurately. This touches on deep questions about the relationship between mind and reality, between consciousness and the physical world. Are mental concepts like mathematics and logic merely useful fictions, tools our brains created to help us navigate the world? Or do they reflect something objectively real about the structure of reality? When we discover that nature follows mathematical laws, are we discovering something about nature, or are we just describing nature using mathematical language we invented? Most physicists lean toward mathematical realism, the idea that mathematics describes something real about the universe. The laws of physics are mathematical, and they work the same everywhere, suggesting that mathematics is built into reality rather than imposed on it by human minds. But this raises new mysteries. If mathematics is real and independent of human thought, where does it exist? In what sense do mathematical truths have being? These are questions that blur the boundary between physics and metaphysics, between science and philosophy. Consider the specific case of Saturn and what we know about it. We know its mass, radius, and composition. We know the structure of its interior and atmosphere. We know about its rings and moons and magnetic field. All this knowledge comes from observations and measurements, but it's mediated by theoretical frameworks, by models and equations that we use to interpret the data. When the Cassini spacecraft measured Saturn's gravitational field and magnetic field, it collected data, numbers representing forces and directions and intensities. Scientists then used mathematical models to infer what Saturn's interior must be like to produce those measurements. The metallic hydrogen layer, the core composition, the helium rain, all of this is theoretical interpretation of observational data, not something we've directly observed. But we have good reasons to trust these interpretations. The models are based on well-tested physics, thermodynamics, fluid dynamics, quantum mechanics, general relativity. When we use these theories to make predictions, they turn out to be correct. Cassini's observations matched theoretical predictions with remarkable precision, giving us confidence that our understanding of Saturn's interior, even though we can't see it directly, is approximately correct. This is how science works. We build models based on fundamental principles. We use those models to make predictions about what we should observe. We test the predictions through observation and experiment. When predictions match observations, we gain confidence in the model. When they don't match, we revise the model or develop new theories. It's a process of gradual refinement, getting closer and closer to accurate descriptions of reality. But there's always uncertainty. Our knowledge is always provisional, always subject to revision in light of new evidence. We might be missing something important about Saturn's interior. Future observations might reveal structures or processes we didn't anticipate. This is the nature of scientific knowledge. It's the best understanding we have based on current evidence, but it's never absolute or final. This provisional nature of scientific knowledge sometimes troubles people. They want certainty, definitive answers, absolute truth. But this expectation is unrealistic. The universe is vastly complex, and our knowledge is limited by our observations and our theoretical frameworks. We can have high confidence in some things, reasonable confidence in others, and we're uncertain about many things. This gradation of confidence is not a weakness of science, but a strength, a realistic acknowledgement of the limits of human knowledge. And despite these limits, we've learned an astonishing amount. We know more about the universe now than humans knew just a century ago, let alone a millennium ago. The pace of discovery has been extraordinary, accelerating as technology improves and our observational capabilities expand. We've gone from barely knowing what stars are to understanding stellar evolution in exquisite detail. We've gone from thinking the Milky Way was the entire universe to discovering billions of galaxies scattered across observable space. We've gone from wondering what planets might exist beyond Saturn to discovering thousands of exoplanets around other stars. This progress gives us reason for optimism. The questions we can't answer now might be answered in the future. The mysteries that puzzle us might be solved by the next generation of scientists using the next generation of instruments. Quantum gravity might be figured out. The nature of dark matter and dark energy might be revealed. We might find life elsewhere in the solar system or detect signals from alien civilizations. We might develop theories that explain the fine-tuning of physical constants or discover evidence for the multiverse. Or perhaps some of these questions will remain forever beyond our reach. Perhaps there are fundamental limits to what beings like us can know, limits imposed by the speed of light, by the horizon of the observable universe, by the impossibility of observing certain phenomena directly. We might have to accept that some things will always be mysterious, that complete understanding is impossible, that wonder and curiosity will always have objects to contemplate. Either way, whether we eventually know everything or whether mystery always remains, the quest for understanding is valuable in itself. The process of discovery, the intellectual adventure of exploring reality, the satisfaction of learning something new, these are worthwhile regardless of whether we ever reach a final endpoint. Science is not just about accumulating facts, but about the journey of discovery, the human capacity for curiosity and reason, the ability to work together across generations to build collective understanding. And you've participated in this tonight in your own small way, by contemplating Saturn and the cosmos, by thinking about storms and atmospheric layers and planetary formation and stellar nucleosynthesis and cosmic evolution. You've engaged your mind with ideas and facts and questions that connect you to the broader human project of understanding reality. You've stood in a long tradition of people who looked up at the night sky and wondered, who built instruments to see farther and deeper, who developed theories to explain what they observed, who shared their discoveries so others could build on them. This tradition continues. Young scientists right now are analyzing data from the James Webb Space Telescope, the most powerful space observatory ever built. Seeing galaxies so distant, their light has been traveling toward us for over 13 billion years. Observing the universe when it was young, barely a few 100 million years after the Big Bang. They're discovering things that will change our understanding of cosmic evolution, of how the first stars and galaxies formed, of how the universe has changed over its long history. Engineers are designing new space missions, planning to send probes to explore ocean worlds like Europa and Enceladus, to search for life in places we never thought to look just a few decades ago. They're developing new technologies to study exoplanet atmospheres, looking for biosignatures, for signs that life exists beyond Earth. They're working on gravitational wave detectors that will let us observe cosmic events we couldn't see with telescopes, like colliding neutron stars and black holes. Theorists are developing new mathematical frameworks to understand quantum gravity, to explain the early universe, to unify the fundamental forces. They're working on problems that might take decades to solve, building on the work of previous generations, knowing that future generations will build on their work. This is the cumulative nature of science, each generation adding to the structure built by previous ones, slowly assembling a more complete picture of reality. And all of this connects back to Saturn and its storms. Understanding Saturn requires understanding gravity and thermodynamics and fluid dynamics. Understanding how Saturn formed requires understanding stellar evolution and nucleosynthesis and planetary accretion. Understanding Saturn's moons requires understanding orbital mechanics and tidal heating and possibly astrobiology. Everything connects. Nothing exists in isolation. Each piece of knowledge illuminates others. Each discovery opens new questions. Each answer contributes to the larger edifice of human understanding. So when you think about Saturn's storms, you're not just learning an isolated fact. You're touching a thread in a vast web of knowledge, a thread that connects to countless others, all woven together into our current understanding of the cosmos. And that understanding, incomplete as it is, represents humanity's greatest intellectual achievement, the collective work of thousands of brilliant minds over centuries of effort. You're part of that too, not as a professional scientist perhaps, but as a conscious being capable of understanding and wonder. The fact that you can comprehend what scientists have discovered about Saturn, that you can grasp concepts like metallic hydrogen and atmospheric convection and planetary formation, this makes you a participant in the human project of understanding. You're taking knowledge that was hard-won through observation and reason and making it part of your own understanding. This is what education is, what learning is, taking the discoveries of others and incorporating them into your own mental model of reality. You're standing on the shoulders of giants, as Newton said, seeing farther, because others have built the foundation you're building on. And when you share what you know with others, when you explain something or teach something or simply express wonder at something you've learned, you're contributing to the collective human understanding, keeping knowledge alive and spreading it forward. And perhaps most importantly, by wondering and questioning and seeking to understand, you're honoring what's best about consciousness, about the human capacity for thought and reason and curiosity. You're using your brief moment of awareness not just to survive and pursue pleasure, but to contemplate the cosmos, to understand your place in it, to appreciate the magnificent complexity of existence. This is meaningful. This matters. Not because the universe cares whether you understand it, but because understanding is intrinsically valuable to conscious beings like yourself. It enriches your life. It expands your perspective. It connects you to something larger than yourself. It gives you a sense of wonder that everyday concerns often obscure. It reminds you that you're part of something vast and ancient and beautiful. And now, having spent this time in contemplation, having journeyed from Saturn's storms to the farthest reaches of physics and philosophy, having exercised your mind and your capacity for wonder, it truly is time to rest. You've engaged deeply with ideas tonight. You've thought about things most people never think about. You've contemplated mysteries that have puzzled the greatest minds in history. You've connected with the grand narrative of cosmic evolution and your place within it. That's a good night's work. That's meaningful engagement with existence. And now your mind needs rest, needs to process and integrate what you've contemplated, needs to prepare for another day of consciousness and activity. So let it happen. Let the transition to sleep occur naturally and gently. The universe continues its eternal processes. Saturn's storms rage on in the cold darkness of space, 1.5 billion kilometers from where you rest. Winds howl, lightning flashes, convection cells rise and fall. The planet rotates, completing another day every 10.5 hours, as it has for 4.5 billion years. The rings glitter in reflected sunlight, billions of ice particles each on its own independent orbit. The moons circle endlessly in their gravitational dance, Titan with its thick orange atmosphere, Enceladus with its geysers spraying water into space, dozens of others both named and unnamed. All of this continues whether you're awake or asleep, whether you're conscious of it or not. The cosmos doesn't need your awareness to exist. It simply is, vast and ancient, governed by laws that operated long before consciousness emerged, and will operate long after the last conscious being fades. And yet consciousness, your consciousness, gives meaning to it all, at least from your perspective. Without awareness, the universe would still exist, but there would be no one to know it exists, no one to understand it, no one to appreciate its beauty and complexity. You are one point of awareness in this vast unconscious cosmos, one brief spark of consciousness in an ancient universe, one arrangement of atoms that can contemplate atoms. This is extraordinary, however it came to be, whether through inevitable physical processes or improbable accident. You exist. You are aware. You can understand. These facts are remarkable, regardless of their cosmic scale or duration. And now it's time for that awareness to temporarily cease, for consciousness to fade into sleep, for your brain to enter the maintenance mode it needs for health and function. This happens every day, as natural as breathing, as necessary as eating. Your body knows what to do. You don't have to try to sleep or force it to happen. Just allow it, let it come naturally. Trust the process. My voice is nearly gone now, fading into the quietness, being replaced by the brown noise that will accompany you through the night. That deep, constant, soothing sound will be your companion in sleep, masking any disruptive noises, maintaining the peaceful environment your brain needs for proper rest. Let it wash over you like waves on a shore, like wind through trees, like the patient turning of planets around stars. There's nothing left to think about, nothing left to understand, nothing left to contemplate. You've journeyed from Saturn's atmosphere to its core, from the solar system to the galaxy to the universe, from physics to philosophy to the meaning of existence. You've wondered and questioned and learned. You've exercised the remarkable human capacity for abstract thought and cosmic perspective. You've participated in the grand project of consciousness, trying to understand the reality it emerged from. And now you rest deeply, peacefully, completely. Let your body relax into the bed. Let your breathing slow and deepen. Let your mind become quiet and still. The transition to sleep is happening, inevitable and natural. Don't fight it. Don't think about it. Just allow it. You are held by reality at every scale. Quantum fields support the atoms that make up your body. Chemical bonds hold those atoms into molecules. Molecular structures form the cells of your tissues. Organs work together to maintain your life. Your body rests on a bed, on a floor, on the ground, on a planet held together by its own gravity. That planet orbits a star held together by nuclear fusion and gravity. That star orbits a galactic center with millions of others. That galaxy moves through space with billions of others in a universe that's been expanding for nearly 14 billion years. All of this supports you, holds you, contains you. You're not separate from it. You're part of it, woven into the fabric of existence, a temporary but integral feature of the cosmos. And right now, part of the cosmos is going to sleep, is transitioning from waking consciousness to rest and renewal. The brown noise continues, constant, calm, eternal in its steadiness. Let it be all you hear now. Let it fill your awareness, pushing out thoughts, replacing activity with stillness. Just the brown noise and the darkness and the gradual fading of consciousness into the peaceful void of sleep. Sleep well, sleep deeply, sleep peacefully, and may you wake refreshed and renewed, carrying some echo of tonight's journey, some sense of the vast and beautiful universe you're part of, some appreciation for the gift of consciousness and understanding. But now sleep, simply sleep. The storms on Saturn continue their eternal dance. The universe evolves according to ancient laws, and you, having contemplated it all, now rest, peaceful and still, part of the cosmic story, a brief but beautiful chapter in the ongoing narrative of existence. Good night.